There it is. It's recording. There are no other participants because I haven't sent an invitation. Okay. All right, let's let it run. See what happens. All right. So we need to do a little review, perhaps, with for chapter 4 and 5, and our exam will be on Tuesday. Okay. Oh, you need another copy.
Yeah, of the periodic table one.
Okay. Let me see if I got one with me. Everybody's here. That's good. I think this is one. Yep.
Thank you. I will use pencil this time.
Yeah, you can use colored pencils.
I've used, like, it looks bad. I mean, and then I got confused and put one of the colors for the halogens and especially for the noble gases. I was like, see, I'm gonna get a new one.
It's probably a good idea when you first see something like that, is to read through the entire thing and get a big picture of it, then go for the details.
Yeah, I was going about one by one, and I was like, I didn't mess
Because,
this up.
for instance, there's one item in there that says all the solids use black lettering. But then when some of the solids, you want black lettering, but you also want that
Man-made,
the hollow
the
outline
like
type.
bubble letters.
It's still black, but if you know in advance that it needs to be outlined, then you don't have to go in and make corrections. And then you want to do all those inputs of symbols and atomic numbers first, then go back and color over.
Yeah.
Otherwise, your pen might not go through the coloring.
Yeah.
So when does the extra credit stuff have to be turned in?
During the exam Tuesday? Yeah. Or by midnight. Okay. So what's bugging you? Are you good with your symbols? Like the ones that I told you to memorize? Got those down?
The next few days to make sure.
Okay, that's good.
I'm having trouble with the binary compound, the type 1, type 2, and type 3, and how to
Okay.
write them out when it tells you just like what's the correct formula for so and so.
Okay.
I'm just having issues with
Example.
that.
Which is a good problem to work on. That's later, isn't it?
84.
Huh?
84.
84. Okay. 84. What's the correct formula for barium hydroxide? Let's see. Blue will probably pick up better on that. Black will pick up better. So if you want barium hydroxide, first thing you want to ask yourself is, where do they come from? Right, where does barium come from? On the periodic table. Right here.
It's
In the second.
metal.
It's a metal, it's an alkaline earth, and only one possible charge.
Okay.
Right. Can't be anything else. How about hydroxide?
It's hydrogen oxygen.
It's a polyatomic. Okay, polyatomic means that it also only has one charge. Like that. It should be in the useful information. Right? There should be a table in there with all your polyatomics. Learn how to find and recognize your polyatomics. That's important. Then all you have to do is balance the charge. So if that's a 2+ and this is a 1-, Polyatomics, you can't split them up. That negative charge is distributed over the whole thing. So if you want more negative charges, you need more whole units. So Ba OH in parentheses subscript 2 will answer that one. Now this is just for information, this is a type 1 because of that. Okay. Okay.
Now, one of the, you said you told us the main, what symbols did you tell us?
I gave you a handout for that, didn't you?
Okay, so the ones you gave us? I didn't know if you went over something too fast.
Oh, no. All right. No, it was that handout with the, all right, I have the extra one. There it is. It's this one. With the red outlines and this kind of pink bin. Those are the only ones you need to memorize. You need another copy? So you don't have to look for it. That's about half of the periodic table. Right, so if there are 118, that should be 59, roughly. Okay. Another one. How about the one right below it? Lead 4 nitrate. Okay. Where does the lead come from? Well, when you see a name like this, and it's got a parentheses with it, you know that that's a type 2. Automatic. So you know you're going to have lead that's a 4+ charge. Right. And it comes, just for point of information, it comes from right here. So it's not a transition metal, but it's still one of these that has multiple charges. The nitrate. Right. Mm-hmm. Right, polyatomic again. That's better. I'm writing bigger so it shows up better. Okay, so now you know with the polyatomic, you need 4 minuses to balance that. So you're going to have to do this to give you 4 minuses for a polyatomic. Right. You can't go in here and change these. Right. That's a cardinal sin. You go to hell for that. And of course, if you have to write your answer, like in a short answer, of course, with multiple choice, you just select it. But if you have to write your answer, then you don't have to put the charges in. I just do that for accounting purposes.
Did you record the lecture you did do that?
No, this is my first attempt.
Oh.
Sorry. Okay. Any others?
We're gonna do 86.
86.
I know this stuff changed up a little bit.
Oh.
It's acids.
Names of acids, yep. HNO2. So I think the best way to do acids is first name your compound as if it's not in solution. Right? So in this case, we would say hydrogen nitrite. NO2 is nitrite. Polyatomic. Then to name the acid, ites become us's for the acid name. So it would be nitrous acid if you put it in solution. Okay?
So you drop the hydrogen part.
Right.
Where it's an acid.
Right, and it has oxygen in it. So you don't say hydro,
Mhm.
right?
If it has oxygen.
If it has no oxygen, then you start with hydro. Like for instance, this one. So that one would be hydrogen chloride as the gas, and then put it in solution would be hydro. And ides become X, hydrochloric acid. Okay. I personally think that the type 1, type 2, type 3 naming convention is fairly straightforward. It's when you get to the acids that things start to turn archaic. Some naming conventions are grandfathered in. And that's unfortunate, but we have to live by the rules from the parent organization, IUPAC. They're like gods. Okay. All right. Any others? We want to do some more acids? Or
89.
89, okay. The correct name for an aqueous solution of HCN. Okay. Remember the trick I told you about? If you have 3 or more elements and one of them is an oxygen, suspect polyatomic. This is one that doesn't have oxygen, but it is a polyatomic right there. So the gas form of this would be hydrogen cyanide. Okay. If you make an acid out of it, excuse me, that is, you put it in solution, and there's no oxygen, right? So you take ides become X. So you do cyanic acid. Oh no, I'm sorry, hydro. It doesn't have an oxygen in it. Probably wondering what I'm doing. Hydrocyanic acid. Because there is no oxygen, you say hydro. I don't think there is a compound that would allow you to do cyanic acid. Yeah, so that doesn't even exist. Hydrocyanic acid for that one. Any others? There's a bunch of them in here. The ones that might give you cause is if you find one like this, like 99 that says, which of the following is incorrect? So then you got to go in and look at every one of them. At least, but if you have a compound for each A through E, then all you have to do is start at the top and go down until you find the one that's correct. I mean incorrect in this case. Find the incorrect one, then you're done. It's the ones that come down and say E says 2 of the above, something like that. Then you got to go through the whole thing. Test-taking techniques. Right. So in this case, you want to do that one. Does anybody have trouble with that one?
Yeah.
Okay.
Which number was it? What's the number of that?
99.
Okay.
Okay, so this one is Li2O, then KLO3, and then KNO3, and then KER, and this one. Okay. Now, rather than using test-taking techniques, I'm going to do all of them. Right, just exercise. How about this one? Lithium comes from the first group, so it's going to be a +1 charge forever and always. How about oxygen? Halogens are -1, chalcogens are -2. Okay? So it's going to be a -2, and you say 2 times +1 balances -2, so that's good. Okay. AlO3. So let's see. Aluminum, where does it come from? All right. This is +1, +2, +3. So aluminum should be +3. The oxygen hadn't changed, it's a -2. So +3 and a -6 don't balance. So that one's wrong. If this were a test, that's where you'd stop. But I'd be just tricky enough to put that one down here. So you'd start and go down. You have to work all the way through. KNO3, potassium, right, from the first group, so it's a +1. Nitrate is a polyatomic ion. It's -1. We're balanced. Right, so that's good. This one hadn't changed, it's still +1. Bromine is a halogen, right? So it's -1. That's balanced. Calcium, where's calcium come from? The second alkaline earth, so it's a +2, or 2+ is the proper way to write it. And sulfate, SO4, is polyatomic with a 2- charge. So that's balanced. Okay? All right.
Now,
Yep.
number 22, I'm guessing that's one y'all went over on today. I missed. Was it talking about Dalton's atomic theory? And I don't have that.
22. Okay. Number 22 says, which of the following does Dalton's atomic theory not address? Okay. So let's think about this. Hydrogen and oxygen gas combine to form water. Dalton's theory says that when a chemical reaction occurs, all that happens is you rearrange the atoms. So A would be true, right? Because you get hydrogen gas plus oxygen gas yields water. And, well, after we balance it, of course. Now you just take 4 hydrogen atoms and 2 oxygen atoms, and they recombine into 2 water molecules. That's it. So A is true. How about B? H2O2 consists of 16 grams of oxygen for every 1 gram of hydrogen. So the hydrogens are 2 times 1 is 2 grams per mole, and 2 oxygens is 32 grams per mole of compound. So the ratio there is 1 to 16 mass. So that's true, 16 grams of oxygen for every 1 gram of hydrogen. And that was also part of Dalton's theory. He was pulling in the law of blank minds. All right. I may as well go back in here and look it up. And be sure I don't have to take my own test. Constant composition. So the law of constant composition says that this ratio is true. And Dalton's theory says that since these atoms combine in a certain ratio, that explains why constant composition is true. See, that's the difference between a law and a theory. Dalton's theory is explaining why constant composition works, because these atoms combine in definite ratios. Okay. C, the relative mass of a carbon atom is about 12 times that of hydrogen. Well, yeah. We know what a hydrogen atom weighs about 1 gram per mole, and a carbon atom weighs about 12 grams per mole. So their ratio is 12 to 1. Or actually, we could say 1 atomic mass unit per atom, or 12 atomic mass units per atom. That's the beauty of the periodic table. Both units of measure are acceptable. So which one you need, right? Most of the time you don't need that one. That's just sort of theoretical discussion. This is the one that we use most often, grams per mole. So the mass number. So if you have atomic mass here, naturally occurring nitrogen is going to be 14.01 grams per mole of nitrogen atoms. Have we gotten to that topic yet? Moles? Okay, sorry. We will, I guarantee it. But Dalton's theory addresses that, and that's another way of expressing the constant composition. Well, not actually constant composition, it's just relative masses. And that's what they knew in those days. All they knew was relative masses, right? If you have a gram of hydrogen, actually they had to study them part of the compounds. So if you had a compound like methane, then you knew that if you had 4 grams of this, you were going to have 12 grams of that. So that's constant composition again. The seat you're sitting on is made up of atoms. Well, yeah, that's true. That's the first premise of Dalton's theory. Everything is made up of elementary particles called atoms. And the second part to that is every element is made up of different atoms than every other element. That's a departure from the ancient Greeks. The ancient Greeks said that everything's made up of the same atom. And we just shuffle them around and we do things with earth, fire, wind, and water to make them change. Now, Dalton said, if you have oxygen, then the smallest part of that element will be 1 atom of oxygen. And it's different than 1 atom of carbon. Then the last one, hydrogen ignites in an open flame, but helium does not. Dalton's theory says nothing about those reactivities. It doesn't explain why why hydrogen burns in air and helium does not. Right? That comes later. We start talking about reactivities, valences, which we haven't discussed yet. But that will hopefully will become clear as we progress through the semester. Why things react with one another. Okay, that was 22. Did I explain the peculiarities of mercury? Mercury is a peculiar element when it combines with other elements. It always combines in, not in pairs. It always combines as a 2+ charge. If it's single, say mercury 2 oxide, okay, this is 2 minus, this is 2 plus, so that's accurate. But if we have mercury 1 oxide, we don't have this. Well, we do have this. Mercury 1 oxide, of course, will be 2 mercuries. That would balance. Where was I going with that? Because that's perfectly legitimate. Well, never mind. It works. Mercury has more than one charge, so it follows type 2. Are you able to count protons, neutrons, electrons, do your ions, how you make an ion? Right, if you have let's take a simple example, like sodium. They have sodium. Neutral sodium atom will have 11 protons, right? Okay, so that means the neutral atom has 11 electrons too, right? But if we make an ion out of sodium, and since it's in the first group, it's always +1, right? You can't change the protons. Change the protons, you got a different element, right? So we have to change the electrons. So in order to get an imbalance of a +1 charge, you need to have 1 less electron, don't you? So you would have 11 protons and 10 electrons would give you the +1 charge on your sodium. And for instance, when it combines with chlorine to make sodium chloride, what happens is that electron there is transferred over here to the chlorine. Chlorine becomes negative by adding 1 electron, 17. So the chlorine has 17 normally, but if we have 18 electrons, that gives you a negative charge, and it got that electron from sodium. Okay? Now that's not balanced. Now it's balanced. We haven't done balancing equations yet, have we? Okay. I have to stop and remember what class I'm in.
Did you 33?
33? Okay. Well, maybe for the benefit of the recording, I should write the numbers up here. 33. Okay, 33. A certain isotope, X2+. So let's put what we have, what we know up here. We're given X2+, contains 37 electrons and 73 neutrons. What's the mass number for this element? The key is this, right? It's an ion. So if it's an excess of +2 charges, how did it get those? Well, it has 2 extra protons, right? So you need 39 protons, right? In order to give you that 2+ charge. Okay, so the mass number then would be this one plus that one. And that means A, which is our symbol for mass number. We would add those together, and that's what? 1, 2. Times mass unit. Is that the right answer? Okay. That's good to know. I have to check myself occasionally to see if I got the right answer. If my answer jives with the one that's in the key. And over time, I find errors and I correct them. So if this is, say, the 5th or the 6th time that I've cut this course, you're pretty safe that the key is right. Did that answer your question? Okay. Okay, let's see what else we got to deal with here. What if you have, anybody have trouble with 39? How many atoms are represented by one formula unit of aluminum chromate? Now they give you the formula, but what if you're not given that formula? And they still ask you that question. So let's see, 39. If I just say the name, and that name is supposed to be unambiguous, you should be able to write the formula from that name. Okay. Aluminum chromate. Okay, where does aluminum come from? Here. +3 charge. Okay, how about chromate? You have to look that one up in your polyatomic. Right? If it said chromide, it would just be chromium. But chromate means that it's a polyatomic. So you look it up, CrO what? 4? 4. And it's a 2- charge, isn't it? Okay. Okay. So now, this is a unit, that's a unit. How do we balance the charge? Yep. Cross multiply is the easiest way. Bring that 2 over here, bring that 3 over here, but it's got to be outside the parentheses. So now we have the formula that's actually given in the problem. That's how they got it. Now the question is, how many atoms are in that unit? Right? So we got 2 of these. How many chromiums? 3, right? Right. That 3 propagates through the entire parentheses. And how many oxygens? 12. So that's 18.
How do you?
7. 3 times 4. Huh? 3 times 4. So that's 5, so 17, right? So you should have 17 atoms in that unit. Now the reason we say formula unit is this is an ionic compound. So that means that it doesn't form discrete molecules. So when it's in a solid form, there are lots of these and lots of those. And they form a network of pluses and minuses. Like table salt will be right, surrounded by chlorines. But that chlorine will be surrounded by sodiums. Right? It just goes on and on forever. What this says, for sodium chloride, the simplest ratio is 1 sodium, 1 chlorine. So if you add them all up, then their ratio is 1 to 1. That's what the formula means for an ionic compound. So for this ionic compound, for every aluminum you have, 2 aluminums you got 3 chromates in that solid matrix. Right? When we get to molecular compounds, they have discrete, independent units. Water is a good example. It will always be like that, separate from every other water molecule. Right? Now, they do interact, right? But they don't, the bonding is not ionic. Right? We'll talk about that later. This is a covalent bond, and that separates molecular compounds from ionic compounds. It's still a compound. Right? All you need for a compound is to have at least two different elements in the formula. You can have more than that, but you need at least 2. If you have something like this, that's not a compound. That's a diatomic element. Right? And you have 11 of them, I think. No, 11 gases. Diatomic elements. You have 1, 2, 3, 4, 5, 6, 7. You have 7 diatomics that you have to remember.
Did you do number 37?
37, okay.
Shouldn't it?
$37. How many phosphorus atoms are represented by the formula unit of cobalt-2 phosphate? Okay, so they've already given it to us. Cobalt-2 phosphate. That's a 3 minus, this is a 2 plus. That should be the formula, if I did it right. Yep. And the question is, how many phosphorus atoms? Right? So you just need to recognize that inside that parentheses, any subscript outside the parentheses is propagated through the entire unit. So there are actually 2 phosphorus atoms in that unit. There are 8 oxygens and 3 cobalts. That's important to know when we get to the discussion of molecular weights. We're determining molecular weights. Just keep that in the back of your head. You got to be able to count how many of what atom you've got in your compound.
This is what I get for missing.
Did you have car trouble?
No, I had to take my wife to Charleston and Rick Valley.
Ah.
Fix this.
Oh, that's right. You did tell me about that. Yeah, if I had this set up, you know, while she's taking the test, you could tune in with your laptop and participate.
Yeah.
Do you have any other classes that use Zoom?
Not this year. I mean, not this semester.
Okay.
The last 2 semesters.
You do have experience with it then.
Mm-hmm.
That's good. The real problem with it now is that Joycey and I have to share this thing. So if she's got a class at the same time I've got a class, then it's technically hers. So that class doesn't get it from me. Question?
Can you look at 55?
55. Okay. Here we go. 55. How many protons, electrons, neutrons does this thing have? Okay. What is SC, by the way? Right here. I think it's one of your elements. Scandium. Scandium. So they've given you the mass number of scandium. in order to answer the rest of it, we need to know how many protons it has, right? So that's the atomic number. So you find it on your periodic chart. Scandium is 21. In this case, the problem doesn't give you every piece of information you need. You've got to go find this one. Right? So that means you have 21 protons. How many neutrons do we have? (45 minus 21). Right? So that's 24 neutrons. Right? This number is the sum of protons and neutrons. So if that number is the sum, then all you have to do is subtract the part that's not neutrons, and you get neutrons. So we take this is equal to A, which is our abbreviation for mass number, and this is your Z number, which is the protons, and A minus Z is the number of neutrons. Okay, how about the number of electrons? Right? If it were a neutral atom, it'd be 21 electrons, right? But it's not. It has has excess of 2 protons. So it'd be 19 electrons. So 21, 24, and 19. 21. B. Oh, I see. I got them out of order. Yeah. 21, 19, 24. Yeah. B.
Will this periodic table be on the back of the desk like you have it here?
Yes. Let me verify that. There it is. Yep, it's there. And the nice thing about that periodic table is, one of the nice things is, charges are incorporated in each one.
But there's a question on it. When it has more than like, say it has a +2, +3, and a +4, and a +5 charge,
Okay,
how would you find the answer to like what you just did just now?
which
It
one?
has,
For scandium?
no, I don't know what B stands for.
Vanadium.
Yeah. See, I has all them +2, +3, +4, +5.
Those are the most common charges, and you have to deduce the charge from your compound. Or if you're going to write the name of the compound, write the formula for the compound, the name has to tell you what the charge is. So it'd be vanadium, parentheses, I don't know, Roman numeral 2, and then the rest of the name.
Okay.
Yeah. Because there's no way you can tell if you're not told what the charge is, or you're not given the information, enough information to deduce the charge. And that also gets to be a little sticky when you get over here, say with chalcogens. Oxygen, yeah, it's 2-. It doesn't have any other choice. But when you get to sulfur, sulfur can have several charges. But when sulfur is in an ionic compound, that is combined with a metal, it's going to be the negative that's available, the -2. And selenium will be the -2. Those other charges are for when selenium is combined with other elements, and it might be ionic and it might not. So if you have this one, say sodium sulfate, the sulfur isn't necessarily 2- charge anymore, right? You would have to deduce that one. So sodium is +1. So 2 times that is 2 pluses. This one is 2-. So that balances the charges. But within that, the oxygens are 2 minus, so that's 8 minus for the 8 minus for the oxygens, but you need to hold 2 of those minuses out for the total, right? So you really only have to balance a 6 minus from within the polyatomic. So the sulfur in that case is 6 plus. Let's see, is that a possibility? Yeah, that's a possibility. See, so, and you don't have to remember that for this test. We'll get to that later, hopefully. I'm just trying to explain why those multiple charges for the elements that we're saying that the chalcogens are 2 minus, right? That's only for, say if we have this, sodium sulfide, then the sulfur would be 2 minus. No other possibility.
Okay. Can we do maybe like 58 or,
58, okay.
yeah, just how many electrons are present in a 10 atom with a mass number of 119? We just did something.
Okay, 58. Yeah. All right. Let's see, what's the question? How many electrons are present in a 10 atom? So what's the symbol for 10? Remember? Can you find 10 on the chart? It doesn't start with a T. Right, SN, or stannum. That's Latin. A mass number of 119. Okay. Blue smoke. That doesn't matter. Mass number has no bearing on the electrons. Only the charge and the element itself. Right? So 10, you have to look it up. 10 has 50 protons. Right? And it doesn't say it's an ion, so you have to assume it's neutral. So that means it has 50 electrons per atom. Okay, that's why A is the answer. That's the way word problems work. Sometimes they give you lots of extra information that you don't need, just to see if you know what information you do need. Okay. I think the term for that is insidious. How about 61? You got all that information in 61. The average mass of boron atom is 10.81. The average mass. So what does the average mean? It means you've taken isotopes of boron, and you've taken the mass number from this group of isotopes, you've taken the mass number from this group of isotopes, and you use a weighted average to give you that number. Right? So if you were able to isolate one boron atom, what are the chances that the mass of that boron atom would be 10.81? 0. It's a weighted average of all the atoms. So none of them are going to be exactly 10.81. Some of them will be 10, some of them will be 11. You might even have a 9 or a 12 in there, but there won't be very many of them. Most of them will be 11s. probably, because if you go from 10 to 11, then it's weighted heavier toward 11 than it is toward 10. So 11 is probably the most common isotope. Tricky question. Okay, are we still recording? We are, we're still recording. That's amazing. I thought it was going to kick out at 45. Well, it's just about 45 since we started this thing.
Oh, yeah. Number 70, I'm gonna try to, I know we just did that over here on number 55.
Oh, you want to see if you can do it?
That's why I wanna.
Okay,
We
no,
put
that's
in the
fine.
spotlight. But,
No, you don't have to come up here. I'll just put up here what you tell me to do.
oh. That's,
So what are we dealing with? P31?
mhm.
Sounds like a fighter plane. Oh, it's P52 or P47s or P38s.
See, this is one of those, I don't know which one.
Okay, what is it asking you for?
It's asking for the proton, electron, and neutron.
Proton, electrons, neutrons, okay.
I see that
Can you tell how many protons that is? How many protons are in that? What is P?
it's over here on there.
Phosphorus, right? So how many protons are in phosphorus?
I'm off.
You want to open it up? Open up the floor.
Yeah, somebody else.
How many protons are in
I know
phosphorus?
it's 31 minus 15 and to get the,
Phosphorus is 15.
yes.
So that's the number of protons. Is it neutral? Yes. So 15 electrons. Right? Because they balance. Now, how many neutrons?
16.
Right. 31 minus 15 is 16. Probably know it better than you think you do.
Yeah, I'm just, I'll get numbers for it, it's easy. And my microscope,
I put you on the spot.
yeah, I felt speech twice because I wouldn't get up with those speeches. I just can't, my heart starts beating real fast.
Okay. Let's see. Let's be sure we get everything that we're interested in.
Can we look at 18?
18. Okay.
Just, if I had a little star next to that.
Okay. 18. Which of these are isotopes of hydrogen? First of all, if you're going to have an isotope, you got to have the same element for every one of the isotopes in your group, right? So you can go through here and eliminate a bunch of them. A can't be because it's hydrogen helium. E can't be because there's no such symbol. HY is no symbol. So it's either B, C, or D. Well, B is carbon, C is potassium, so D is the only answer. That's the only one that can be hydrogen, right? So what are these called? They have names. We didn't go over it in class. This is deuterium. And this is tritium. Okay. They're only important where for nuclear physics is involved. You've heard of heavy water. Heavy water is composed of, I think, some of this and some of that as water, but the isotope then would be either 2 or 3. It's Probably this one, tritium's probably the one that's, and heavy water is valuable in a nuclear reactor because it more effectively absorbs neutrons. Right. That type of hydrogen is also valuable in nuclear reactions. When we put hydrogen in a, let's see, there are two technologies that are used for fusion energy. One is called the Tokamak. It's like a big magnetic donut. And the magnetic field in there keeps the hydrogen away from the walls of the container because they're going to be millions of degrees and they just melt right through. So you confine them with a magnetic field. Well, they use these two isotopes because they more effectively combine to make helium and give off energy. The other one is the, I don't know what they call it, the laser machine. It's got 96 lasers that are pumped to high energy, and then they're all focused on one point inside a big sphere. Right? So they time it. So this little pellet containing these two hydrogens drops, and when they hit the center, they fire the lasers. And the energy from all sides heats that thing up, plus it adds compression, and you get your fusion reaction. Those are the two main technologies. That's because those two guys out in Colorado that said they could do it cold fusion, they were lying, and they eventually lost their jobs. Now, I'm not saying cold fusion couldn't be done at some point in the future, but not with our current technology. I just wonder, the name cold fusion implies that it happens at low temperature. But the whole point of fusion is to get lots of energy, right? So once you start your reactor at cold fusion, it's going to heat up really fast. So it's not cold anymore, right?
Cold start.
Yeah, they'll have to pick a different name then. All right, cold start. Yeah, cold start.
Okay,
Yes, sir.
I know, how do you know something's positively, negatively charged or if it's neutral? By these numbers over here. This has got me really confused. I see all these numbers and it's got me confused.
In the periodic table,
Yes.
those charges are only useful if you're talking about a compound using those elements. If the element is written by itself and it has no charge explicitly given to you, like this one, and say, it's like that, it's neutral, no charge. But if it's like this, it has a charge,
Okay.
right?
So it's whatever's written on the paper here, like number 70, when we were doing it just a second ago. It was neutral because it didn't have no plus or minus whatever. Okay, right?
Right,
Okay.
right.
Okay. That's what I was trying to figure out how I was gonna figure it out.
No,
With all those on there.
the only time you can deduce a charge for one that's not explicitly given is if that element's in a compound.
Okay.
Right? If it's in a compound like this, then you know it's charged, like that. But if it's sitting out here by itself, you got to say what it is. I miss those little details sometimes because I've just been doing it for so long.
Yeah.
So you have to stop me every now and then and ask these questions. Well, let's see. Oh, we got plenty of time. I just want to be sure that we don't run out of time and haven't covered everything that you want.
So number 73, you would define the hydrogen atoms, you need to find for the hydrogen, right? It'd be 4 times 2, maybe
Right.
4 times 2.
And
plus
then
8.
plus 8, exactly. So it'd be 16, right?
Okay.
You got 8 and 8, 16. Yep, you got 8 and 8, 16. Yep, that's right. That is correct. Let's see. We'll be sure that we cover all the topics adequately. Okay. So if you've got a compound and you're trying to decide how to name it, first thing you do is say, what are the two parts of the binary? Is it a metal and a non-metal? If it's a metal and a non-metal, then it's either a type 1 or a type 2. Because type 3s are non-metal, non-metal, right? So now that you know, say it's a metal and a non-metal, it's either a type 1 or type 2. Then you look at the metal and say, where does that metal come from? Is it from a place in the periodic table where it can only have one charge, no other charge? If that's the case, then it's a type 1. If it's not from those places, then it's a type 2 because it has multiple charges. Then when you name it, you've got to put it in parentheses and say, what's the charge on that metal? That's your decision process for naming compounds.
Could you do maybe 101?
Yeah, sure. 101. Okay. So the formula for the compound formed from the okay, they're telling us to put two polyatomics together. So they want to combine this one and this one. Okay? Got to remember your rule. When you're combining polyatomics, you don't mess with the subscripts on your polyatomics. Right? If you need more than one of them, you got to use parentheses. So we're going to balance 3 minus with 3 pluses. That means we need 3 of those because 3 times that plus is 3 plus. And then they balance. They cancel out. Yeah. Ammonium phosphate. That's pretty good fertilizer, actually. You can buy that in the bag because it gives you the nitrogen that your plants need. It also gives them the phosphorus they need. Right there in the same thing. Doesn't give them any potassium, but it does give them those. Potassium's not as big a problem in this state as nitrogen because the soils are so thin, and phosphorus because they're acidic and they have lots of iron in them, aluminum. And iron and aluminum take phosphate into a compound that's insoluble and then just sequester it away from the plants.
Why is chicken? So it's like chicken poop.
Uh-huh.
It's very good to use, but if you use like, say you got a gallon of water, you're only supposed to use like a little pellet of it.
Uh-huh.
And if you use any more than that, it'll burn things up. I use it.
It's the salt effect, right? If you have if you put something on them that is has a high salt index, we call it, then it will damage the cells, right? It's an osmotic effect. In other words, if you have, say, salt water, and you stick your hand in it, just leave it there for maybe a half hour, it'll come out wrinkled.
Yeah.
Because it just draws the water right out of your cells. So yeah, I used to have a garden on my supervisor's property when I lived in Baton Rouge. And he had 100 head of cattle, so we had lots of poop. So every once in a while, we'd take his tractor and a flatbed and go out there and just he'd drive real slow, and as he was going along, we'd fork the cow pies, throw them up on the thing, and then we take them back to our garden. We wouldn't put it right on the garden because it had a salt load in it, right? Because he fed the cattle hay, they ate grass, and he also had a salt lick for them, right? So their feces would have a load of salt. So we dump them off at the corner of the garden and leave them there for maybe a month. Because the rainfall in Louisiana, that part of Louisiana was like 60 inches a year. So it didn't take long. Yeah. And they would just wash the salt out of them. Then we could take them, throw them in the garden. Good to go.
Oh, yeah. What do you think about the pole? I know this has nothing to do with the pole shift. Do you think it's going to happen?
Pole shift?
The magnetic pole, they're saying it shifted.
Oh, yeah, it's always been moving.
Is it?
Yeah.
So that's true.
Yeah, and over the millennia, right, over geologic time,
Yeah.
it has flipped several times. North, south, south, north.
Would be bad if it does.
I guess there are some scenarios where it could be, but as long as we have a magnet in the middle of the earth, then we have that magnetic umbrella that keeps the solar wind away from our atmosphere. That's the problem. If we ever lose that magnetic bubble, then the solar wind will strip our atmosphere away and just, that's the end of it. Yeah. Same thing, that happened to Mars, they think. Mars doesn't have a magnetosphere to protect it. So over time, the solar wind just blew their atmosphere away. Blew its. Yeah. I talk as if there are Martians up there. That salt index also goes for wood ash. Some people like to put wood ash in their gardens. A little bit's okay because wood ash is basic, and if your soil's acid, it'll neutralize it. But you got to be careful because of that salt index.
Yeah.
So you'll burn your plants to pieces.
Now, on this extra point stuff you're doing here.
Yeah.
You're having us to do.
Sure.
You want to take it as far as the guy that gave us here. What if we don't, our writing's not that good, like, I'm just sloppy writing.
Well, if I can read it.
Okay.
You want to, we were talking about that before you came in, I think.
Yeah, are you wanting us to number it just like you have it right here and everything?
Well, just follow the directions.
Okay.
Yeah. I gave you that new periodic table because it is complete. It has all these empty spaces filled with elements. They all have names now. You don't have to put the names, just use the symbols. And you're going to put the numbers, rather than here, you're going to put them down here. The reason I want you to put them in the lower left-hand corner is because that's the position reserved for atomic number, lower left. Okay. Periodic tables, they put them all places. I'm just trying to get you used to writing it the conventional way. It's a good idea for you to go through and read all your directions because some of them overlap. We were talking about that earlier. Where the solids, I want you to put them in black. But then the man-mades are going to be in outline form. Like, for instance, let's see, where's a man-made? Plutonium. So instead of writing like this, you'll write it like outline.
Yeah.
Let's see. Something like that. Okay. You may have to do some research to find it. All the information you need is not necessarily on that periodic table. Okay, let's see. let's go back to, let's do 147 and 148. NaHCO3. Na 147. HCO3. Okay, want to name that. Where does this one come from? Group number 1. Plus 1 charge. How about this one? That's a polyatomic, right? And it's not just this one that's a polyatomic, it's the whole thing. Right, so look in there and find HCO3.
Hydrogen carbonate.
Hydrogen carbonate. So it has a -1 charge, right? Okay, so they wrote it correctly, that's good. Now we just name it. Sodium, hydrogen, carbonate. That's the beauty of polyatomics. The name is the one that you just slap on the board. You don't have to say I'd or ick or us or whatever, unless you're going to make an acid out of it, of course. Now, this is the proper name, the IUPAC name that's currently favored. You may also see it like this. Sodium bicarbonate. This is what they call a trivial name. It's ancient, but they still use it on packaging, right? So you pick up Arm & Hammer, right, in the yellow box, look on the back of it, and it'll say sodium bicarbonate. But that's what it is.
Yeah, they've got both of them on there. One in parentheses.
Okay. Okay, so now for 148. 148? Yes, 148 is this one. Now, the giveaway for this one should be those hydrogens. This is an acid, right? So you want to name it as if it weren't an acid first. Then you can transform that into the acid name. So this would be hydrogen is only 1 charge. So you don't have to say dihydrogen. Say hydrogen. And then what's this one? Polyatomic.
Carbonate.
Carbonate, yeah. Hydrogen carbonate. Now we're going to make an acid out of it. So put it in solution. And this has an oxygen in it, so we don't say hydro. We just take this part of the name, and H's become what?
Acid.
All right, H's become X. So it's carbonic acid. That's it. Okay. Now,
If they gave us that and it didn't say it was an aqueous solution, and they said the name.
if you write the name out yourself, right, you could write this. If they say aqueous, then it's an acid. But if they don't, then you can write it out that way and I'll accept it. Of course, if it's multiple choice, you pick the best answer. Everybody in here drink pop? Pop, pop, pop. Okay. You drink that every day. Every time you take a swig of pop, you're drinking that.
That's why they keep it with.
That's part of the reason. It's a complex solution. But this one, all they do is dissolve carbon dioxide in water, right? So if you take carbon dioxide and put it in water, you get 2 hydrogens, 1 carbon, 3 oxygens, carbonic acid. Now, it doesn't like to stay in solution, not at the concentration that they want it. So that's why they do it under pressure. And then when you crack the lid, it pops. Now, the real reason that it eats your teeth is not, this is not the major culprit. The major culprit is this one. Phosphoric acid. If you read the label, you'll find phosphoric acid there too. Should be. In fine print. But phosphoric acid is very aggressive toward the calcium in your teeth. And it forms calcium phosphate, which is not part of your teeth. It's in solution and you swallow it. So, yeah, if you drink a lot of pop, that'll happen. Phosphoric acid is also good if you're a farmer and you have a rusty gate. You can't just paint over it. Remember, I mean, anybody here live on a farm or know a farm? Okay. Okay. Just ask the farmer if they ever paint over a rusty gate. They'll tell you, are you crazy? If you paint over a rusty gate, it's just going to keep rusting right on underneath. You got to convert that rust to something that's more stable and not reactive in the atmosphere. So take that and combine it with phosphoric acid, and you make, let's see, this is Fe3, it's 3 plus. You make iron phosphate, and then whatever you have left over. Let's see, I paint myself into a corner here. Iron phosphate. Oh, it's probably water. But you convert, that's not balanced. But you convert that iron oxide into iron phosphate, and iron phosphate is very stable. It will not revert to rust. So you convert all that to iron phosphate, then you can paint over it. So they have this, I wish I could remember the name of the stuff. I think it was green colored. They colored it green, just so you see the difference. But it's kind of a gel mix, and it's got phosphoric acid in it. So you don't want to paint your hand with it. But that way, since it's in a gel, you can stick your brush in there and you can paint your fence with it. You just leave it on there for 30 minutes to an hour, let it do its thing. And then, I'm not sure if you wash it off or not, or you could just paint right over it. You have to ask that farmer. Yeah. You'll know what you're talking about. Yeah. He or she, I don't know. It's he. Okay.
I take care of the 4-H camp over in Walton County.
Oh, okay.
Yeah. So, big old piece of property everywhere.
Right.
So,
I guess if you had a, I don't know, a tin roof or tin siding on a shed, you do the same thing. I mean, it's covered in tin, but underneath is steel. So once the tin, if the tin ever gets scratched or beat with something from the outside and opens up a pore, then starts rusting, and you can just slap that stuff on it, and then actually you could just leave it there. It's very stable. It'll sit there. I mean, it's better if you can paint it, but I mean, it still does the job and stops it from rusting sealed it up. Let's see. Well, I don't see.
Can we maybe do number 150?
Sure.
So,
Yeah. So 150 says what? The charge on a strontium ion in its ionic compound. Okay, so let's find strontium. Gotta find out where strontium is. SR, right over here. So what group is it in? Yep, so that means it's, right. Okay. And since it's an alkaline earth, that's the only charge it ever has. +2. Wow. I wonder if they gave me a pro account. Because it's still recording. If they gave me a pro account, that'd be great.
if I knew that's still recording, I probably wouldn't have talked. Ask questions about it. I thought you said after 45 minutes, it stopped.
I thought it would. But we'll see. It's a good test to see if this microphone picked everybody up. And these speakers are not doing what they're supposed to. I don't know if we need to change something in here to connect to them. Let's see. Oh, they're not even plugged in.
Oh.
That's why. Here it is. I'll have to try that later. Run the test and see if it works. Oh, the microphone's not even plugged in. What in the world is going on? Joycey? I depend on you. It's depending on the speakers and the microphones from the laptop. So maybe it'll pick you up well. And you won't. We'll see. Doesn't have a timeline, so I don't know. Probably an hour. Time signature to see if the sound changes. We shall see. This is a test. I used to do field research. Field tests on farms. And then robots start to water. Cars. Here you go. Look, they but I never wrote it. I was out in the field, rain,
change. Not real. So I feel wrong. Stuff is and worse, you just made. I was carrying. I need my hands to carry up. Take pictures. On flags. And I noticed over time. Summer. So I get in my book and I see parts of it. Definitely all three. I look like I do this. People that especially in that thing is it's just the way my mom is. So she learned. Yeah, get over on the other side. Smoke beats in. Then you get to the point. Now, Carolina, well, brothers do. Barbecue. Yeah. Just cut it into the steak. Grind up the chicken. Once you start that, yeah. Probably. I did my math research. Yeah, no. When you cook crawfish, you would take that. Say, the new commercial operation. Full painting that, package it up, and treat. So it's good quality. Get it from what about wretch, figure out all that waste. Reuse it. Quality food. Especially sand, those types of fish that deposit the color like a shell, then deposit those reflection. One. Farm raised sand. These that have it in like hard to sell. That's sand. That look like sand. Farm raised. We're developing diets incorporating waste. What just big waste material? Very high. Like steam, roll, fry, break, break off, take fish, store, plates. Or we had the spaghetti machine. Squeeze your 9 ounce of hole, and then you do rotate and cut. Spray gun. Huge. Empty up on the ladder. Lots. big old cylinder. Air is heated, it's floating in a cycle. So it has pumping material, hot, sort of floating, and heated air, cycle it, make dust. Right. Free.
It's the same thing. We have a problem. His family. They learned it from someone up there that lived down south. There's people graded here, but they're not fishing. Not fishing. And they do it. Sausage. Onion, all kinds of stuff. Like everything. And it feeds and it's been huge. Compared to mine, and compared to mine, big. There's just family Christmas, all that. So it's a lot. Like they do sometimes. But now they have gotten into the new age and they have these big old cookers that they use.
Propane.
And they're huge. Like they'll do it on Labor Day for a week and stuff like that. It's good.
Yeah. All that stuff. Good. That's the problem. Yeah, I see. Yeah, that's got to go through the shed. And then massive. Rockfish. Then more. And actually, at that point, we didn't put on the finish the oil, and then we take the whole thing, dump it into the styrofoam. And then you take the solid seed, take this down, and close it, let it steam like that. Yeah.
You pay like that. So you because I use like I love he hates he has gastro problems. He hates because I'm all like chilling about he goes to something that's takes like a whole thing of Asian. He says it's good, but it messes with me.
Yeah, I can't tolerate that seasoning with vegetables.
He's like,
Used to be back then. Okay. We still see it in the okay. We're back.
we talked about trying to get my nursing degree and go to school and everything. One trap, first place I want to go to. There's a company down there that works for me, and no matter what, like whatever year it was, they're going down there for 8 years. They're like come down here and be an electrician. And so I told him, I said I could do all the most. I go more money than most people make, like double recruitment a year.
Yeah.
Because he was understand that they like it. It wasn't like an electrician picking up something out of here, training it with a family, they can train it. They department. And they're like, so we like the young electricians.
Well, it's pretty short. 9:30, 11:20, so